Hi, welcome back. We were discussing about electromagnetic induction. We saw that how Faraday and Henry across two continents in England and in US conducted various experiments on how magnetism and electricity are related. Now, taking forward from what Oersted and Ampere did, uh, Faraday and Henry actually worked on the other way around, like instead of electricity to magnetism, magnetism back to electricity. So they found out fundamentally some new laws which tell us that how uh, the flux, which are basically rate of change of flux, is what the electromagnetic force that is induced. I mean EMF induced. Uh, so now the question is, we also talked about this statement that E that gets induced is actually minus of d phi by dt. So this is what we wrote down. Okay, and if you are using a wire with this multiple turns, minus n into d phi by dt. Now we said that this minus n, minus sign, is because it is in the opposite direction. Okay, what is the meaning of this opposite direction? So that is what Lenz's law talks about, and why it has to be. Why is it such a common sense that it is opposite direction? So that is what we are going to now understand. Okay. Now let us say that I'm going to have a coil. Okay. Yes, I'm going to use this as a coil. Okay. You can say I wound a coil around it. Okay. So this is coil. Now you can see this very well, and this is my magnet. Okay. Like exactly like how you're keeping it here and using the magnet like this. Okay. So now the point basically is, when I actually take my magnet, okay, and insert it inside this. Okay, let us assume that my magnet is basically this side. This side is north. Okay, you can see that this is actually not a magnet, but assume that this side is north and this side is south. Okay, so if I take this north inside like this, okay, how can I say what is the direction of the magnetic field? That is what I want to now figure out. Okay, and I will use Lenz's law to figure out. Now before going to that, okay, I'm going to basically have certain conventions very nicely understood. Okay, so that is basically what we talked about as the right hand thumb rule. Okay, right hand thumb rule is a very nice rule to understand the direction. Okay, so suppose if I have a nice if I have a wire which is conducting some certain current, okay, let's assume that this is my wire. Okay, so the current is actually going from bottom to top. So now if I want to find out what is the direction of the magnetic field around this there will be magnetic field. Okay, so I will use this technique. Okay, that is, if the direction of current is in this direction going down to bottom, I use my thumb to show that direction. Okay, so this, if it is going down, this is the direction. If it is going up, this is the direction. So I will keep the thumb like this and use my fingers to hold it like this. Now the fingers actually points. These are all my arrows of my fingers. Okay, the finger points, the way it is curling it, that points the direction of the magnetic field. That means magnetic field around this is like a circle. Okay, and at every point its direction is what my hand fingertips are showing. So here the cause is the moment of the current. Okay, and the effect is the fingertips showing it. So this is showing the cause and this is showing the effect. So that means cause is the current and effect is the magnetic field. So this is where I use the right hand thumb rule. The same right hand thumb rule, I am going to use it in a different way in the case of a circular coil. Okay, let us say my coil. Okay, see, here actually, if you ask a question, for example, if a wire, okay, if a wire is carrying current, what is the magnetic field around this? We will find out from here. Okay, assume that this wire is carrying current like this. Suppose if I have connected battery and wire is carrying current here. Okay, so now I can use right hand thumb rule. How I'll use? So let us say I will take this path with this side of the story. Okay, this side of the wire. I'll use my thumb here, okay, and I keep it like this. My thumb is like this. Thumb is showing the direction of current. These fingers are showing the direction of the magnetic field. Okay, that means magnetic field is going inside here and coming out here like this. Correct? Now, if I go current flows like this, and in this portion, current is going down. So my thumb has to show down, and I will hold it like that. So that means magnetic field is going inside and coming outside. Like it is how the magnetic field is. What about the downstairs? Okay. Current is coming here. So I will actually hold my thumb in this current direction like this. So now I will put my finger around this and it is going like this. So magnetic field is going inside and coming outside. So here also magnetic field is going inside and coming outside. Here also going inside and coming outside from here. Here also it is going like this and coming out like this. From the top it is entering and from outside it is coming like this. That is how the magnetic field is. Here also you can see the current is going this way. So I will hold it like this. It is like this. So once you understand that, I have used exactly the same thumb rule to figure out actually the magnetic field direction here is always going inside, and all the other points magnetic field is coming outside. Okay, so that is how we figure out. Okay, what does that mean? That actually means actually going inside and coming out like this means that if you can actually put instead of this, put a magnet like this is my magnet. Okay, so instead of that I have put a magnet, and that magnet has north. Okay, you can see north, and from north to south it is going. So north to south it is going. So like this. So generally if you write it, okay, it is always like if you have a north and south, this is how the magnetic field's direction is. Okay, you can say that inside the magnet it goes from south to north. So outside it goes from north to south. So now inside this we saw that it is going inside like this. So it is as good as keeping a magnet here. Instead of this we have kept a magnet here. Then also it is going from south to north inside. So like this. So saying that a coil is kept like this, where current is going in this direction, okay, is same as saying that I'm going to keep a magnet like this, which north on the other side, and getting the magnetic field lines like this. These two are actually exactly same things. So a coil like this carrying current is same as a magnet like this. See this? Coil like this is same as a magnet like this. Now in that scenario, okay, I also use another nice technique to find out, see, the direction of this magnetic field. Now this shows the north, no? Left side minus, this side is north, this side is north. Okay, so now to get that north direction for the coil, I use another simple same right hand thumb rule in a slightly different way. I'll show you how I do it. Okay, it's a slightly shortcut of the right hand thumb rule. What I will do is, now I know the current is flowing through like this. Okay, now I am now going to use my fingers to show current. See this, my fingers to show current. This is not the same thumb rule. Thumb rule slightly modified to give you a shortcut to this only in the case of a circular coils. Okay, so I will show this like this. This is my, I hold it like this. Okay, fingers like this. And where is my thumb showing? My thumb is showing inside. If I put my fingers in the path of the current, my thumb is showing inside. So that means that my thumb is now showing the direction of the north of my dipole. What do we call this? Magnet. Okay, it's like this. So that is an easy way for me. I just take this, where which direction current is flowing, I ask. Let us say current is flowing in this direction. In that direction, I will put finger and my thumb shows directly the north. Or if the current is flowing like this, I will put it like this, and when my thumb is showing this side, so north is pointing this way. So I just established to you how I will quickly find out, given a certain current through a coil, where is the direction of the north that it produces magnetic field. Okay, we know that current produces magnetic field. Now the question is this cable, this coil which I am holding here. Yeah, I am going to basically get my magnet inside this. Okay, so question is, if I simply keep it here or keep it here, there will be no magnetic field. If I just push it here, there is magnetic field. There is change in magnetic field, and hence there is current. Okay, now that change in magnetic field, how the magnetic field is changing, let us understand that. Let us say my magnet is approaching. So when it is approaching nearby, magnetic field for this whole whatever is linked with this uh, inside this coil is actually increasing. If you see this, okay, it is in this direction. Okay, it is in this direction because north is this side. Okay, and it is increasing. So north is this side and it is increasing. Okay, see, remember this. Okay, so when it is increasing, what is the direction of uh, what should be the direction of the current that gets produced? So the answer says, Lenz's law says the answer. It produces current inside this coil in such a way that it opposes whatever the change is happening. So let's understand this. Whatever the change is happening, it opposes that. What is the change that is happening? Change that is happening is when you're bringing it nearby, okay, the change that is happening is increase in the magnetic field. Now, how do you oppose it? By decreasing the magnetic field. Okay, when you are bringing in, okay, as your hand is making this, you are actually increasing the magnetic field. Now, this circuit produces inside such a current to oppose your move, to oppose your movement of a magnet, which is increasing the magnetic field. How do you oppose that? Now, if you produce a magnet, let us say, okay, if it is north facing, north is this side, it is moving towards this. Now, if you produce a magnet inside this, which is also showing north, like this, okay, that would repel. So, if I have a magnet like this, and if I have another magnet which is having a north this side, and north to north, if I bring it nearby, it opposes, it pushes this, it repels it. So if I can produce somehow, if this circuit somehow produces a magnet in this direction, okay, in this direction, okay, that means it is going to push the whatever original magnet that we are sending. That is how it can oppose. So how does it produce a magnet in this direction? So how to produce a magnet in direction? That means magnet direction should be like this. So if the magnet direction has to be like this, current direction is like this. So I showed you the technique. Current direction is like this, magnet direction is like this. That means it produces a current in this direction. So we can say now, whenever I try to push a magnet here, it produces a current in this direction. This direction. Why? Because that is the way you can oppose it. Do you understand that? Whenever you actually send this towards this, it produces a current in this. This is double level logic. Please understand this. Okay, if you understand this, your Lenz's law will become very easy. A lot of questions from the competitive examination can be answered very easily. Okay, so the moment you bring it nearby, it produces a magnet like this so that it can push it out. How does it produce a magnet? By actually sending current through this. The current that gets induced basically is in this direction. If this direction is the current, this direction is the magnet, and that magnet actually pushes this magnet, and hence it opposes your movement. So now we understood. An approaching magnet with a north in the side this produces the current in this direction. Got it? Now let's go and understand it a little better. Okay, next step we will see. Now what is the situation when I'm putting inside already halfway through and going away. I'm going away now. You see what is happening when I'm going away. Okay, the magnetic field is weakening, so my motion is changing the magnetic field, but it is weakening the magnetic field because you're going away. Now the way it gets generated such that it will try to oppose the weakening of the magnetic field. That means it will try to create a magnetic field in the same direction to strengthen it. It has to create a magnetic field inside this direction. So do that. How do I pass the current? To get magnetic field in this direction, I have to pass the current like this. Now, so it generates a current in this direction. So if you are actually taking this like this, it generates a current in this direction, so that it can create a small magnet inside this, which would strengthen the magnetic field. Okay, so in the sense that if it is going this way motion, okay, you can see that it is going that way, you would want to stop this, you want to make sure that it doesn't go away. Okay, you have to oppose its movement. How do I do? Look at this, this is having north here and south here. Okay, and now it is going away. So to attract this, I need a north, because this side is south, this side being south, I need another one here which is a north. So like this, if it is going away, I need another one here to attract this another magnet should have this side north, because this is south and this is north, and this north is going to be unlike pole for this, and it attracts this. Okay, if we can produce an imaginary magnet inside this coil, okay, with a north this side, it would slow down this movement. Okay, it will pull it towards itself. So hence it has to produce a magnetic north on the other side. So if I keep it here, current will flow like this. In the first when it is moving towards this, we had to produce like this and current flowed in this direction. Now when it is the same motion, it is going like this, now the current actually is produced in the opposite direction. So just by putting the magnet inside this, in the beginning the current is flowed in this direction, and when it is moving away, the current is flowed in the other direction, once like this, once like this. So that is how you can predict the current using Lenz's law. So now once you did that, the question that comes is, now why does it happen like that? What if it had produced some other way, opposite direction? Just imagine what it would have happened. What would have happened? Okay, look at this. Let us say if you got it up slightly slowly pushing it like this. Okay, you are here and you are moving towards it. Now instead of opposing it, let us say if it has helped it to move, in the sense that if it had created a magnetic field in the same direction which pulls this also inside. Okay, so that means current would have generated in this direction. To generate the magnetic field like this, current would have generated in this direction. If that had happened, if in the world, in the nature, if nature had done that, you know what does it mean? That means if you are bringing like this, and if you just leave it here, it will be pulled inside. It will be pulled inside continuously. So what would happen then? That means that something is moving now without any energy. That means some energy is getting generally created with no apparent reason. So that is not law of conservation of energy. So whenever law of conservation of energy says that the energy has to convert from one to the other form only, it cannot get created. Here what is happening is that continuously this is getting pulled inside, and when it's going there, it is pushing that side. So if you just come here and leave it here, it should go like this on its own. If Lenz's law was not right, it would have actually helped it go along. And if it had helped it go along, that means that without energy, things started moving. There is no energy and the magnet is moving. It cannot happen. Law of conservation of energy says that only if there is energy, it can move. Otherwise, it cannot. It cannot create energy from nowhere. So it would have violated the law of conservation of energy if Lenz's law was untrue, but Lenz's law is true. So that means that it always opposes the whatever the cause it is. It opposes the cause. Let us go and see solve some problems, and we will get to know what is the meaning of opposing the cause. Okay, so how it the direction of the current that gets produced, or direction of EMF that gets induced, actually opposes the cause of that gets produced. And if you just know this much, this one statement of Lenz's law, most of the questions in competitive examinations can be solved regarding the direction of the induced EMF or current. Let us see how with some 2 or 3 simple questions. Now, figure shows planar loops of different shapes. Okay, moving out of or into a region of a magnetic field, which is directed normally to the plane of the loop away from the reader. Okay. Now determine the direction of induced current in each of these loops. So now what is happening is there are current loops. Okay, this is one of the loops, nice rectangular loop. Okay, so now what you see here, these are all not dots, these are actually crosses. Okay, this is one of the conventions. Whenever we write a cross, that means magnetic field is going inside the board. Okay, the direction. If I write a dot, magnetic field is coming towards us, okay, outside the board. Now in this case we have put crosses, that means magnetic field is all directed inside the board. Now what is happening is this small circular loop, the rectangular loop, it is entering here into the magnetic field, so perpendicular to the magnetic field. If the magnetic field direction is in this direction, okay, and this actually is entering the field, magnetic field, like this. Okay, so now perpendicular to that. So the question now is that when it is entering like that, how is the direction of the current? Okay, what is the direction of the current? Now the direction of the current, when you say, the answer can be like this: it is going in this direction or it is going in this direction. So you just have two options, whether it may be doing A D C B A, or it is A B C D A. These are the two options. Okay, so in one option it is going like clockwise, in another option it is going anti-clockwise. Which is the right answer for the first one, for this one? Okay, let's see what is the right answer. Okay, and we will use Lenz's law to figure this out. Okay, so what is happening is it is coming from outside, okay, where there is no magnetic field. There is no magnetic field here. You can see this area, there is no magnetic field. It is entering, and in the area of magnetic field it is entering. So now if you see the amount of magnetic field inside this, inside the area covered by the circuit, okay, inside this, is it increasing or is it decreasing? It is increasing. More and more area is getting filled by the magnetic field, so it is increasing. So the magnetic field is increasing, and this is the direction of the magnetic field. Okay, if magnetic field increasing and this is the direction of magnetic field, if you want to oppose that, okay, not you, basically the current gets generated happens to oppose us. So now our logic goes from the other side. If it has to be opposed, how the current is got produced? So logic is in the opposite direction, but actually what happens is in this direction. It produces current first, which opposes the magnetic field. Okay, our thinking logic is in the ulta direction. Okay, uh, it is like a crime scene investigation. All the crime scene is already over, so you go there and see, oh, this is like this, that means he would have done like this. So that kind of a thing. Okay, so now the what you will see here is how do I weaken the magnetic field? the magnetic field is in this direction. If I produce a direction of magnetic field like this towards you, it weakens the magnetic field. So to produce this direction of magnetic field out like this, what should be the direction of current? See, it is like this. Now the direction of magnetic field has to be like this, correct? So this is our north, like this, the direction of magnetic field. That means to be get the direction of magnet is from inside out like this, I keep the thumb in that direction. Now I see my fingers are going like this, so that means the current has to be like this. So like this, A B C D E A. If the current is in the direction of A B C D A, then it will produce a magnetic field from inside out, which would weaken the existing magnetic field. Why should it weaken the existing magnetic field? Because by moving so, we are actually strengthening the existing magnetic field. So it should do the opposite. So it should weaken the existing magnetic field. So that is why it produces in the direction of AB, BCD, ABCD, correct? ABCDA. So that is the direction. A, B, C, D, A. This is the direction. Okay. So if it goes in this direction, it produces the magnetic field in this direction, which opposes the existing magnetic field. That is how you can figure out. So the answer to this question is the current gets produced in this direction. That means like this. This is the direction. Now let us look at what will happen to this one, second one. So this small loop is going away from the magnetic field. If the small loop is going away from the magnetic field, then this much area, what is it covering, that is actually inside that the amount of magnetic field that it contains is decreasing. So to be able to oppose that, you have to make a magnetic field such that it doesn't decrease it. How it doesn't decrease? By adding some extra magnetic field in the direction of magnetic field which is already there. So if I produce a magnetic field inwards, okay, then that would make sure that the magnetic field is not decreased that much. It is opposing the decrease of magnetic field. It is not going to completely compensate for it, but that is the direction. Okay, so it basically tries to oppose it. When that happens, it has to produce magnetic field in the inner direction. So thumb inside like this. So that means it produces magnetic field current in this direction, which is BCDA. BCDA. That is for the second one. So you have to do it by yourself to know this. Okay, which direction magnetic field is there, which direction movement is there, is it increasing or decreasing magnetic field? If it is decreasing, how to increase it? If it is increasing, how to decrease it? In order to either increase or decrease it, what is the direction of current? And that direction of the current is the direction of the current, the induced current. That is like 4 levels of logic your brain has to think without making a mistake in any one of those levels. Okay. But when you start doing it by practice, it becomes very simple gradually. Okay. There is no other math involved in this. Now here you see, it is actually going away. Going away means it is going away from the magnetic field, which means the magnetic field is decreasing. If the magnetic field is decreasing, to oppose that, increase the magnetic field. To increase the magnetic field, direct the magnet in the same direction as what it is already there. So you have to direct the magnetic field this way. That means it has to be like this. That is the magnetic field direction. This is the loop. So if it does do like this, it will generate like this. So this is A, B, C, D, A. A, B, C, D, A. This also. One very important thing that you have to understand here. Okay. Let's say this is moving like this. After it enters the magnetic field, when it is going inside the magnetic field, continue to go inside the magnetic field, the amount of magnetic field inside that does not change. so it doesn't produce any current. Okay, while it is traveling in the magnetic field, none of these loops, current loops, none of these circuits produce any current. So the current is produced only if it is leaving the loop or it is entering the loop when the flux linked with that coil or flux which contained in that coil changes, because only change can produce induced current. Okay, so in this case the change is happening only when it is either entering or when it is leaving, not when it's traveling in the middle of the path, middle of this. How much ever coil you take here and keep moving inside this area, nothing happens, because the flux that is contained by that coil is not going to change, it's going to be same. Okay, so this is one nice question where you get straight some understanding of how to use Lenz's law. Okay, let's look at one more. Look at this. Okay, a closed loop is held stationary in a magnetic field between north and south poles of two permanent magnets held fixed. Can we hope to generate current in the loop by using very strong magnets? See, it's just this. There is a magnet, closed loop is held stationary. Okay, so you just take a closed loop. Okay, this side on magnet, this side on magnet, very powerful magnet. You hold it here. Will it generate magnetic electricity in this? Because the magnets are very powerful. No, we said that no, how much ever powerful it is, unless it is changing, it doesn't generate any electricity. Okay. So the answer is no, we can't be hopeful of that. The next question is, okay, a closed loop moves normal to the constant electric field between the plates of a huge capacitor, a large capacitor. Is a current induced in the loop when it is wholly inside the region between the capacitor plates? Look at the understand the question. Okay, a closed loop like this, okay, moves normal to the constant electric field. So there is an electric field, okay, I'm going to write here electric field, and this is, I'm going to write electric field like this, dots, not magnetic field. Remember, this is electric field. What is the meaning of dots? Electric field is in this direction. Okay, and a closed loop, I will take a closed loop. It moves normal to the constant electric field, normal, like this, between electric field, between electric field between the plates of a large capacitor. Okay, so how did this electric field come about? That is by keeping two plates of a capacitor like this, and there is an electric field in between. I'm going to move like this in the middle of the two capacitors. Plates, these are two huge capacitors. Okay, in the middle of that, perpendicularly like this, I will move one coil like this. Okay, I hope you are able to picturize that. Now, is a current induced in the loop when it is wholly inside the region between the capacitor plates? So between the capacitor plates, if it is there inside, this is one plate, this is one plate. Okay, this is in the middle here. It is moving. Does it induce? Uh, does it induce basically some current through that? That is the one first question. Okay. Second question is, when it is partially outside the plates of the capacitor, the will it induce? Will it induce? That is the question. Now, what do you think? So now, when this is uh, not a magnetic field, yeah, it's the electric field. So now, when the electric field is there and you are moving this, will it induce? This question, what did Faraday say? Faraday said that if there is a magnetic flux that is there, okay, and if that magnetic flux is actually uh, changing with respect to that, if the magnetic flux is changing with respect to the conductor, then only it is going to induce. So we were discussing about So when it is there in the electric field, will it actually produce any current? When it is in the electric field, it cannot produce any kind of induced EMF, because Faraday only talked about magnetic field. If there is a magnetic field, and in the magnetic field, if you move a circuit, it will produce. But if it is electric field and if you move it, it will not produce. So the answer is, in both the cases, it does not produce any current. Okay, this is not Faraday said. What Faraday said. Okay, then. So let's take another one. A rectangular loop and a circular loop are moving out of a uniform magnetic field. This is a uniform magnetic field. Now we're back to magnetic field. So a circular loop and a rectangular loop, both of them are moving out of the magnetic field. Okay. Uh, to a field free region with a constant velocity v. Both of them are going with a constant velocity v. In which loop do you expect the induced EMF to be constant during the passage out of the field region? The field is normal to the loops. Very interesting question. So this is one level of extra thinking that you need to do. Okay. So when it is going out of this loop, how much electric field is reducing depends exactly on how much area is reducing. Because what is electric flux? Flux for us is nothing but B dot A. Okay, dot, because if since it is both of them are perpendicular to each other. Okay, the direction of the area and the B both are like, one area is like this, B also like this. So there is no angle between them is 0. Okay, cos 0. So we can simply say B into A. Okay. Now if you cos B into A, if you say, what is A? A is nothing but, let us say this is um, breadth and this is height. Okay, so breadth into height. So B, breadth into height, BH. Now we know that it is going with a constant velocity. Okay, if it is going with a constant velocity, anyway, when it is going out of this, the height is not changing, only breadth of the area which is basically inside this is changing. Because even it goes here, this height is same, the breadth is only this much. So this area only comes into picture. This area is outside, doesn't come into picture. Okay, so that breadth basically is changing with a velocity v. Okay, the breadth is changing with a velocity v. That means that actually it is nothing but the area. How much area is changing? Let us see. The area, this is phi. Okay, d phi by dt is equal to, okay, b is not changing. Okay. So d into d of area, that is bh by dt, which is b into d small b into dh, sorry, d into small h to dbb by dt. So what I am doing is that whatever is changing, only I am taking the derivative of that. Okay, b and h are not changing, only the breadth is changing. So this dv by dt is nothing but the velocity, if you think about it. Okay, that is the speed with which it is moving. So that can be taken as velocity, vh into v. Okay, so induced EMF is this when it is going out. So induced EMF means what? The velocity is changing. How it is changing? It is velocity is actually constant, if you think about it. Okay, it's a constant velocity. So while it is moving away here, during that time, it is a constant velocity. So that means if you actually plot it, okay, assume that you are plotting time versus the induced EMF. Okay, so initially when it is traveling inside, there is no change. So you will get a zero, basically zero EMF. Okay, and when it starts actually getting out, then what happens is the current that is there is a change that starts producing. It's already there is a change that is proportional to the velocity. Okay, so the change that gets produced will give you certain EMF, and that EMF actually becomes constant like this. Okay, constant because V is constant. So how fast it is changing, the area is constant. Okay, and hence up till this distance that finishes off, it will be like this, and then again it will become 0. 0 because once it is fully out, then again there is no change. Now think about this. How much will be the width of this? So this is basically the distance v divided by the velocity. Okay, b by v. This is b by v. Distance is equal to time into velocity. Okay. So this is the distance v by v. I'll write it here. V by v is the duration, not here. Okay. Okay, this height is actually bhv. This is how it changes in the case of a rectangle. So how does it change in the case of a circle? Let's see. Okay, in the case of a circle also, okay, we are going to have this as area, but area here is basically the pi r square, okay, is the area of the whole circle. Okay, however, when it is going out here, the way it is going out, the area of how much is remaining or how much is going out here is definitely not varying linearly with time. You see, though circle is moving linearly with time, the area initially what goes out is small. Okay, that means the decrease in area initially is small, but when it is becoming, it is slightly more outside, more and more area gets outside. Okay, in a small amount of time. See, if I'm going to write here, you will get a better picture if I write here in a slightly big way. Okay, so I will take a few snapshot of time. I'm going to basically say that this is my area of where the B is there. Okay, and circle is basically like this circle. Okay, now R, if you take the same this one, after some time it will be basically like this. Okay, after some time it will be like this. After some time again it will be like small one, basically like this. It's all moving in this direction. So let us say the distance that it covers from here to here is same as here to here. So the velocity is constant. So when I am going to take basically a small amount of delta t, okay, let us say first 1 second, 1/10 of a second. First 1/10 of a second it has moved out. Next 1/10 of a second we move out the same amount. Okay, but the area that gets reduced in that time is not the same amount. The area that gets reduced is this much. Next time that the area that gets reduced is this much. Next time that the area that gets reduced, for example, is this much. So that means that the area that gets reduced is actually increasing. So in given time, that means rate of change of area or rate of change of flux linked with the area. Okay, that rate is increasing. Okay, till it goes to half. Afterwards, the rate is actually decreasing. The rate is proportional to the area, decrease in area. So it is decreasing. So if I want to plot that one, okay, it will look like anything till it goes out, it is 0 only. Later also it will be 0, but in between it will not be constant. What it will be is initially it is increasing, and later it is actually decreasing, like this. Okay, exactly the how curve looks like. Will it look like this or will it look like this? Okay, these things are the questions that you can figure out by actually finding out the area, writing the equation and see how the curve is. So that is outside the scope of this question. In this question, they are only asking, okay, where is it constant? Okay, this is constant only here. Here it is varying. Okay, that's all we need to know in this question. Okay, so that actually gave us. I think there may be just one more question. Okay, so in this question, let us say. So in this question, predict the polarity of the capacitor in the situation described by the figure. Okay, in this figure, if you see carefully, we have put a loop like this, but there is a capacitor, a loop and a capacitor. Okay, now what we are doing is we are actually taking this and bringing them nearby. Okay, if you are bringing them nearby, moving them like this, that means you are inside. If you see the direction of the magnetic field, how is this? This from north to south means direction of magnetic field is like this. Inside the direction of magnetic field is like this currently. Okay, and you are bringing it nearby. That means you are strengthening this magnetic field. So if you are strengthening that magnetic field, now the Lenz's law tells us that it has to oppose it. And to oppose that, it has to weaken the magnetic field. So it has to produce magnetic field in this direction. Okay, so to produce magnetic field in this direction, it has to produce current like this. Sorry, this magnetic field, current like this. It has to provide current like this. So to do that, basically, the A has to be positive and the charging has to happen like this. A has to be positive and B has to be negative to get that direction of current. Okay, to get this, if you get this direction of current, what will happen? So you keep on charging this, this will become positive, and this, so you're basically making the current flow like this and make that A become positive, and the other will, this one will become negative, B will become negative. Okay, that's how you can actually figure out the direction of current and direction of charging and all that using our Lenz's law. Lenz's law basic idea is whenever the magnetic field changes with respect to a coil, either because of the motion or because of the changing the current somewhere in the magnetic field producing circuit, so it will produce a certain current and EMF. And what is the direction of that? It will be in such a way that it opposes whatever caused it. Okay, that is the whole idea. And how it is conservation of energy and all we discussed. Okay, next we will talk about, in the next class we'll talk about what we call motional electromotive force, in the sense that we say that if you try to move, let us say, this rod on this, which has a magnetic field here. Okay, so there is a change in magnetic field with respect to this particular loop, the area changes, so that brings about a certain current that is induced in the circuit. Now how do we explain that? Using the things that we already know. So like, for example, Lorentz force. Okay, is it possible to explain it using that? So these are the things that we are going to look at in the next session. Thank you.